is evaluated as integral minus infinity to plus infinity x of t dt. Is that clear? So the area under the signal gives you the DC component of the spectrum. So this is a very important result. Remember, the area under the signal is the DC component of the spectrum. Likewise, the area under the spectrum gives you 2 pi times the value of the signal at t equal to 0. So these two are very important takeaways from the second question that we are undertook. So please remember these questions, these results. Now we will move on to some problems on finding inverse Fourier transforms. Like for example, we will try to find out the inverse Fourier transform of x of j omega is equal to j omega by a plus omega the whole square. X of j omega is equal to j omega by a plus j omega the whole square. So we already have this result. T e raised to minus 18 into u of t is Fourier transform to 1 by a plus j omega the whole square. So now from the frequency differentiation property, you are multiplying this by j omega, right? This is being multiplied by j omega. So to give you the spectrum given in the question. So from the frequency differentiation property, you have d by dt of x of t is Fourier transformable to j omega into x of j omega. So I have written this as an inverse Fourier expression. Fourier inverse of j omega and x of j omega is equal to d by dt into x of t. Or here in this question, if I take this as x of j omega into 1 by a plus omega the whole square, that is here, would be Fourier transform to d by dt of t e raised to minus 18 d of t. So this you evaluate as a product rule. So when you evaluate this, you get it as minus 8t into minus 8t e raised to minus 18 plus e raised to minus 18 into 1, the whole into u of t. That's equal to e raised to minus 18 into 1 minus 18 into u of t. So that is the inverse Fourier transform. Okay. So that's very easily done. Now another question is to find out the inverse Fourier transform of instead of j omega is equal to 1 by j omega into j omega plus 1 plus 2 pi delta omega. So this uncannily resembles our integration property. Mind you, I proved this integration property after discussing the Fourier transform of the unit step function, which is the integration property is written here, integral minus infinity to t x of tau d tau is Fourier transform to x of j omega by j omega. So here you have this j omega plus pi into x of 0 into delta omega. So if you compare these two right hand sides, then see if you can write x of j omega is equal to 1 by j omega plus 1. So for that, x of t would be equal to 1 by j omega plus 1 would have a inverse Fourier transform is equal to e raised to minus t because of this 1 here into u of t. So e raised to minus t into u of t. Is that clear? And to complete this equation, you also need to have this capital X of 0. What is capital X of 0? Capital X of 0 would be 1 by j into 0 plus 1, which is equal to 1. So z of j omega can be therefore written as 1 by j omega plus 1 by j omega. So that is 1 by j omega into 1 by j omega plus 1 plus pi into delta omega. X of 0 is equal to 1. So pi into 1 into delta omega plus again pi into delta omega. So from linearity property, we can find the inverse Fourier transform as a sum of the inverse Fourier transform of these two parts. So this evaluates to integral minus infinity to t e raised to minus tau u of tau d tau, right? Integral minus infinity to t, integral minus infinity to t e raised to minus tau u of tau d tau plus 1 by 2. Why? Because 1 has got a Fourier transform to 2 pi delta omega. Now that is z of t. So this we can evaluate. Your integral minus infinity to t u of tau d u of raised to minus infinity to t u of tau d tau plus 1 by 2. So this we can evaluate. What is u of tau? U of tau is equal to 1 only for tau greater than or equal to 0. So this evaluates to integral 0 to t. So that part you can evaluate. I forgot to complete that question, but we can complete this by evaluating this integral from integral 0 to t e raised to minus tau d tau plus 1 by 2. So e raised to minus tau d tau would be e raised to minus tau by minus 1 between limit 0 to t. So evaluate that. Okay. So next we move on to the next question. Find the Fourier transform of the pulse x of t shown here. X of t consists of a pulse like this. It's equal to 1 for 0 to 1, 2 for 1 to 2, and 0 outside these intervals. So if you solve this in the conventional manner, it's very easily computed like integral 0 to 1 e raised to minus omega t dt plus integral 1 to 2, 2 e raised to minus j omega t dt is equal to this expression. So that is equal to 1 by j omega into 1 plus e raised to minus omega minus 2 e raised to minus 2j omega. So that's easily verified. This part you can compute by evaluating these values. Now the same question can be evaluated in a different manner, which we call as the method of successive differentiation. Now the method of successive differentiation can be applied if a signal can be differentiated again and again until you end up with only impulses. So if you take the derivative, for example, if you take the derivative of this signal, what is the derivative of this signal? This would be a delta t. Here again you have a delta t, and here you have minus 2 delta t. So this is delta t, minus 2 delta t. So d by dt of x of t is this. So delta t is Fourier transform to 1. Delta t minus 1 is Fourier transform to e raised to minus omega. And minus 2 delta t minus 2 is Fourier transform to minus 2 e raised to minus 2j omega. So d by dt of x of t is Fourier transform to j omega and x of j omega from the time differentiation property. So d by dt of x of t is Fourier transform to j omega x of j omega, implying that x of j omega is equal to 1 by j omega into this expression. This is what you got earlier. Okay, this method could be applied because we found out the derivative of the signal to be consisting of only impulses. Okay. Likewise, let us look at this signal. This is a triangular pulse. Take the first derivative. The first derivative is this pulse, a positive pulse and a negative pulse. And the second derivative, here you will have an impulse, unit impulse, and here you have minus 2 delta t, and again here you have a unit impulse. So this is delta t plus 1, minus 2 delta t plus delta t minus 1. This is Fourier transform to, this is e raised to j omega minus 2 plus e raised to minus j omega. Is that clear? So that we can simplify as, so e raised to j omega plus e raised to minus j omega would be 2 cos omega. So that is 2 cos omega minus 2. So d squared by dt squared, d squared by dt squared of x of t would be from the time differentiation property given by j omega the whole squared, which is equal to minus omega squared into x of j omega, where x of j omega minus j omega squared into x of j omega, which is equal to 2 cos omega minus 2. This you have evaluated now. This is equal to 2 cos omega minus 2. So what is x of j omega therefore? 2 cos omega minus 2 by minus omega squared. So that is 1 by omega squared into 2 minus 2 cos omega. Okay. Again, this is fairly straightforward. And the next question, which is to find out the inverse Fourier transform of a signal which is given to you in the polar form. This is the magnitude part and this is the phase part. The magnitude part consists of 4 impulses. So this impulse has got an area equal to 5 pi at minus 4. At minus 2, the area is equal to 3 pi. At plus 2, the area is equal to 3 pi. And at 4, the area is equal to 5 pi. And the angles are minus 60 degree at minus 4, plus 30 degree at minus 2, then minus 30 degree at 2, and plus 60 degree at 4. So 30 degrees pi by 6, 60 degrees pi by 3. So therefore the spectrum can be written as 5 pi delta omega plus 4 into e raised to minus j pi by 3 here. So that is this part. 5 pi delta omega plus 4 into e raised to minus j pi by 3 plus 5 pi delta omega minus 2. So this should, sorry, this is 3 pi delta omega plus 2 into e raised to plus j pi by 6. That is this part. Okay. Then here you have 3 pi delta omega minus 2 into e raised to minus j pi by 6. That is this part. Okay. And finally, you have 5 pi delta omega minus 4 into e raised to plus j pi by 3. So I will group it like this. So 5 pi delta omega plus 4 into e raised to minus j pi by 3 plus 5 pi delta omega minus 4 into e raised to j pi by 3, 3 pi delta omega plus 2 into e raised to j pi by 6 plus 3 pi delta omega minus 2 into e raised to minus j pi by 6. Now to find the inverse Fourier transform of this expression, you have to note the following. One is that you know that 2 pi delta omega. So all these are impulses. So therefore you have to find out the Fourier transform of these shifted and scaled impulses. For this you will find out the Fourier transform of an impulse. So impulse in the frequency domain, inverse Fourier transform of the impulse in the frequency domain, that is. So you know that 2 pi delta omega, 2 pi delta omega. So what does it mean? You only have a frequency component at omega equal to 0. So which means that the signal has only DC. We already proved that 2 pi delta omega has got an inverse Fourier transform given by an eternal DC, that is 1 for all time. So from the frequency shifting property, you know that x of t into e raised to j omega naught t is Fourier transform over to x of omega minus omega naught. So therefore 2 pi delta omega minus omega naught should be Fourier transform to e raised to j omega naught t. And 2 pi delta omega plus omega naught should be Fourier transform to e raised to minus j omega naught t. And by linearity, if you add these two, you would be getting e raised to j omega naught t plus e raised to minus j omega naught t. So dividing this by 2 throughout, you can write pi delta omega minus omega naught plus pi delta omega plus omega naught would be e raised to j omega naught t plus e raised to minus j omega naught t by 2 as its inverse Fourier transform. So that is cos omega naught t. So pi delta omega minus omega naught plus pi delta omega plus omega naught is having an inverse Fourier transform given by cos omega naught t. Now cos omega naught t plus theta. So I will expand just here because I already also have these phase angles which are to be accounted for. So I will just put cos omega naught t plus theta and expand that as equal to half e raised to j omega naught t plus theta plus e raised to minus j omega naught t plus theta, which I will expand as half into e raised to j omega naught t into e raised to j theta plus e raised to minus j omega naught t into e raised to minus j theta. And from the definition, e raised to j theta into e raised to j omega naught t, e raised to j theta is a constant. So is having a Fourier transform given by e raised to j theta into 2 pi delta omega minus omega. And e raised to minus j theta into e raised to minus j omega naught t will have a Fourier transform given by, this is a constant, e raised to minus j theta into 2 pi delta omega plus omega. So therefore, if you add these two and divide by 2, this should be Fourier transformable to pi. So since you are dividing by 2, Fourier transform to pi into e raised to j theta into delta omega minus omega naught plus e raised to minus j theta into delta omega plus omega. Is that clear? So now we will compare this with the problem statement that we have here. This is x of j omega. So therefore, 5 pi, you have a constant 5 here. In addition to this, you have a constant here 5. 5 pi delta omega plus 4 e raised to minus j2 pi by 3. In place of e raised to j theta, you have e raised to minus j pi by 3. So this should be e raised to minus j pi by 3. Please read this as e raised to j pi by 3. E raised to minus j pi by 3. Plus 5 pi delta omega minus 4 into e raised to j pi by 3. You will have an inverse Fourier transform given by, since you have a constant 5 here, that will be having an inverse Fourier transform given by 5 into cos. This is for here, so cos 4t plus theta. What is theta? Theta is pi by 3, right? Theta is pi by 3. So from this, e raised to j theta, e raised to j omega naught t, e raised to j theta, e raised to j theta, e raised to j omega naught t. So that is 5 cos 4t plus pi by 3. And the next part would be 3 pi delta omega plus 2 pi by this. Please read this as pi by 6 plus 3 pi delta omega minus 20 e raised to minus j pi by 6. Would be having a inverse Fourier transform given by 3 cos 2t plus minus pi by 6, which is equal to 3 cos 2t minus pi by 6. So in other words, x of j omega is equal to 3 cos 2t minus pi by 6 plus 5 cos 4t plus pi by 3. So that's all about the problems on Fourier transforms. Actually, there is one more kind of problem that can be solved by means of partial fractions, but which we will see after discussing the computation of inverse Laplace transforms using partial fractions. And we will see that Fourier transform is a special case of partial Laplace transforms. And we will likewise evaluate the Fourier transforms by partial fractions after discussing the partial fraction form of solution of Laplace inverses. Okay, so that's all about the problems on Fourier transforms. If you have any doubts, please free to use your WhatsApp group to discuss the doubts. Okay, so everyone please stay safe. Okay, thank you very much. We'll stop now.